Just 1 minute. Okay, yeah. Hopefully more people will join soon. Okay, so we were discussing the ellipsoid method last time, and so what I want to do now is describe some of the details today, and we'll not do the complete calculations because they are just technical, and it's not clear if there is a general principle to be learned, which is relevant to this course. But if you're curious, I would like you to look up Shriver's book, from where I have everything I'm saying has been taken. Okay. So it's just a couple of pages. I mean, just 2 or 3 pages. And if you go through those calculations, you will develop a good idea of how to deal with ellipsoids. Some of it we will do today, but how to do approximations involving ellipsoids, and ellipsoids are not relevant only to the ellipsoid method. At some point, you will be doing probability, and in probability, especially when you use higher dimensional Gaussian distributions, there is a positive semi-definite matrix that comes up, and the calculations that are involved in understanding what happens to Gaussian random variables under various linear transforms are very similar to what is done in the calculations that are involved in ellipsoid method. The other thing is, at some point, you will take Pranab's courses on quantum information theory, and a density matrix in quantum information theory is a positive semi-definite matrix with a certain additional property. And change of basis happens all the time in quantum information theory. So some, what should I say? Some facility with manipulating positive semi-definite matrices will be useful there also. Okay, so if you have time, use this opportunity to look up Shriver's book. So I will just repeat what we said last time. And so we started with a ball. Yeah, we had this unit ball in n-dimensional space, and that was this one. And this we understand. Yeah, it's just defined by the Pythagoras theorem. And we write this Pythagoras theorem in this fashion, because later on, when we generalize to ellipsoids, our equations, inequalities will look very similar to this. Now, this is what we discussed last time. So suppose we have a linear transformation A, which is non-singular. So which takes this, our original space, and probably deforms it into a slightly different space. Yeah. Then what happens to this ball? Now, this ball turns into something like this. Okay. And so if let A be a non-singular matrix, and you map a point, you transform it, you transform it, and you also shift the origin just to be general. But this shift is usually not very serious. Okay, it's just we are trying to keep our center of the ellipsoid general. Okay, for most calculations, it's enough to understand what happens when it is just a linear transformation. The affine part of it doesn't add any complications. So now, if you just rewrite this, so in terms of y, so if x goes to this and we define this to be y, this is the point in the new space, then you can rewrite x as, what should I say? Y minus c, A inverse y minus c. So if you substitute that in this equation, you get A inverse y minus c, and its dot product with itself should be less than or equal to 1. That's what has been written. Now, this central part here is something that depends only on the linear transformation that was used. Okay, and this is a matrix transpose times the matrix. Some matrix A inverse, its transpose times the matrix, and such matrices are positive definite. Sorry, what did I write? Positives. Positive definite matrices, because this is non-singular. And they are symmetric. They're clearly symmetric. Okay, so our definition, basically anything that is obtainable by a linear transformation, or in general an affine transformation. And so we can use this as our official definition of an ellipsoid. So anything that can be written like this. The only thing is, instead of the usual, if it was a ball centered at C, this matrix would have been the identity matrix. Now this matrix is a positive definite matrix, which amounts to saying that a positive definite matrix has this orthonormal basis of eigenvectors. Okay, and all these eigenvalues are positive. So it means what this matrix actually is doing is just stretching the ball in some orthonormal direction. Okay, so it turns out that there was this ball here, and we chose two directions like this. In one of them, we decided to stretch it. In the other, we probably decided to shrink it, and we got this. Okay. So any ellipse is obtained from a ball by choosing some directions and either stretching it there or shrinking it there. Okay. And the stretch and the shrink are actually determined by this linear transformation. Okay. So now let me review our ellipsoid method. So we were given this polyhedron in the form of a set of inequalities, and we are going to assume that it is bounded and full dimensional. Very soon, I mean, maybe in about half an hour, I'll tell you how these assumptions can be removed. And essentially what we are going to say is that if you're given a polyhedron, if it is not bounded, we will be able to cut it off and make it bounded. And if it is not full dimensional, that is, it's lying on some subspace, some strict subspace of the original space, then we'll be able to fatten it, slightly fatten it. And of course, we need to guard against the problems that can arise from fattening. So we'll see about that. Okay. So so let us assume that we look at this matrix and look at the row size. Row size By row size, I mean there is a formal definition, but we will not bother too much about that formal definition. The formal definition for us is that the row size is, or the definition we are going to use is, look at all the all the numbers that appear in the row, look at their binary representations, add them up, and maybe you add one for each entry. So maybe if the row has n entries, first of all you write n plus you look at the binary representation lengths of all the numbers and you add them up. Okay, that we define as the size of the row. So essentially, when you try to store it in a computer, this is the number of bits you will need. And maybe after each number, you will have to put some little marker which says that the next number is starting. And for that, you keep this additional n. Okay. Yeah. So, and let us define this new to be this thing. So it is basically polynomially related to the number of bits in any row of this matrix. Okay. So the first observation is that we have to start everything by putting our polyhedron, which we are assuming is bounded, inside an ellipse. Okay. So in fact, we'll start by putting it inside a ball. And it turns out that if a system of inequalities is bounded and is defined by matrix whose entries are all reasonable, then this entire entire polyhedron is contained inside this ball whose radius is 2 to the power nu. Okay. So the radius is something which itself is a big number. It's a big number. But if you look at the binary representation of the radius, the binary representation of the radius will be nu bits, which is polynomial. Okay. So to begin with, we have only been given the set of inequalities, and our goal is to find one feasible point. Yeah, one point which satisfies these inequalities. Okay. And we start by constructing this ellipse, which is a ball. Okay. And let me just remind you what we do in each step. In each step, we take the center of the current ellipse and we ask, is this center feasible? Okay. If it is feasible, we are done. If it is not feasible, we say, why is it not feasible? And somebody points to a hyperplane which separates your center from the polyhedron. So we translate that hyperplane to this center and say that we are now in this space. And we now enclose this part, the bottom part here, in another ellipse. Okay, perhaps something like this. Yeah, that is our next ellipse. Now that ellipse, its center is not here anymore. Yeah, it's probably center has shifted somewhere in this direction, maybe here. So we ask again if that new center is inside this polyhedron, polytope now. Yeah, bounded. So, and we get an answer. And we keep repeating. Okay. And there were two claims. Okay, so let me just see if I missed anything that I should have said. Yeah, this is fine. Anyway, I said. So there are two claims. One is that there is a significant reduction in the volume of the ellipsoid in each iteration of the program. So each time you do this Kachian step, the volume does reduce. Yeah. I mean, this exponential gives you, it may be misleading. Yeah. So it's not an exponential reduction in the normal meaning of the word exponentially small. It is just barely small, e to the power minus 1 over 2n plus 2. You should really think of this as a number which looks like 1 minus 1 over 2n plus 2. Okay, I'm dropping the higher order terms. So the original original ellipse, the new ellipse is a factor this smaller than the original ellipse. And this is just barely small. But the important thing is that the denominator here is just a polynomial in n, yeah, just a linear number. So if you keep repeating this, then you will be accumulating an exponent here. And once that exponent becomes too large, yeah, a big polynomial in this, then this number will start coming down. Yeah, I mean, will be exponentially small depending on what you put here. Yeah, 2 to the power minus some large polynomial. Now, but always we are maintaining the invariant that the new ellipse that you put. Yeah, so this was the half ellipse, and you put a new ellipse in this case, and the new ellipse continues to contain the original polytope. So how long can you go without stepping into the polytope, without your center falling inside the polytope? Well, if you did too long, your ellipse will be so small that it will not be able to hold the entire polytope inside. And why? Because we also prove that the polytope itself has reasonable volume. Okay, this is something we did last time. If it's a full dimensional polytope defined by equations where the matrix, the underlying matrix AB, yeah, all the entries have bounded binary representations, then any polytope defined by such inequalities has reasonable volume. At least it will be small, exponentially small, but 2 to the power n and nu. So we will adjust our number of iterations here so that it brings our original polytope. What was the volume of the original ellipse? The original ellipse was contained in a box of size 2r. So the original ellipse had this sort of a volume. R itself was just exponential in n squared and nu and things like that. So this was the size of the original ellipse, and that this original ellipse is going to be hit by this number, yeah, exponentiated, I mean, with the big power, and that's going to eat into it, and soon enough it will fall below this, and that would be a contradiction. Okay, so that gives you a bound of polynomial, a polynomial bound on the number of steps needed before you find the feasible solution. Okay, so this is the main idea of the ellipsoid method. So we needed 2 claims. This claim we proved last time. It was just a question about it based on determinants. That is, if you have some vectors which are in general position with the reasonable coordinates, then the parallelepiped described by them, its volume is given by the determinant that you should probably have seen before. But what we are interested is not the parallelepiped, but the little polytope generated by those vectors. Yeah, those vectors. Yeah, those are finally independent vectors. And it turns out that this volume is somehow 1 over n factorial times the volume of the parallelepiped that is generated. This is something you should imagine and check. Yeah. So all in all, we get a lower bound on the volume of the polytope. Good. Now, I would like to give you some idea. Actually, we'll probably do the complete proof of this. So why is it that when you have an half ellipse, there is always an ellipse that encloses this half ellipse, and its volume is this much smaller than the original ellipse? Okay. So consider this special case. Yeah. So I have rotated my picture. I hope it's okay. Yeah. So the half ellipse. So in this case, our original ellipse itself was just a sphere, and the half ellipse that we are talking about is this. And I would like to enclose in it enclose it in a new ellipse and somehow claim that the volume of this new ellipse is significantly smaller. Significant is that same insignificant number. Yeah. So significantly smaller than this original unit ball. Okay. So let us see. So let's, by symmetry, it seems reasonable that when you build the new ellipse, its center should be at some point here. Let us call it -x. Yeah. Yeah. So the original ball was cut by this hyperplane, and this is the part where the polytope is hidden. And we are now assuming that the new ellipse that we want to build has its center here at -x. Okay. So now, last time I said that the square root of the eigenvalues of the matrix D that will define this new ellipse. Yeah. So these eigenvalues are squares of some numbers. And what do these numbers themselves, lambda ones, describe? They describe this so-called the radius, the various radii of the ellipse, that is half the axis length. Okay. So now we have a nice orthonormal basis. So we believe that so there is this little n-1 dimensional space here, which is symmetric, which is parallel to this hyperplane. And then there is this perpendicular direction. And in this direction, the length of the axis is 1 - x. Is this clear? This is x. So this length is 1 - x, and that is half the length of this axis of the ellipse. So at least we have managed to pin down one of the eigenvalues. Yeah. So that eigenvalue squared is 1 - x. Is this much clear? Yeah.
Sorry.
Go ahead.
Could you please repeat that?
So let us assume, or maybe by symmetry, it seems reasonably convincing, that the center of the new ellipse will be at some point which will lie on this line, because this was the hyperplane that cut the original ellipse. So let us say this is the point. And now
so
that
in higher dimension, you are saying it will lie on the normal to the hyperplane.
Yes, because of some symmetry reason, but our goal is to just show that there exists an ellipse whose volume is significantly smaller than this ellipse. So I'm saying consider the ellipse whose center is here.
Okay.
Okay. Yeah, but again, this is something I need your help in. So all the texts say that elementary geometry tells us that the center has to be here, and this is the unique ellipse of minimum volume. So they just don't say that we are giving you an ellipse of this volume, so be satisfied. They are in fact saying that this is the ellipse of smallest volume. I have not been able to verify this, but if you have an idea, I would be curious to know. Okay. So are we okay so far? Yeah. So I'm saying.
So Jayakumar, I have a doubt. So who has given us this ellipse? We have to construct it ourselves, don't we?
Yes. So we have not. So right now I'm saying somebody has told us that here is this unit ball, and I'm going to cut it in the direction perpendicular to the x-axis. And let us just get some practice and find out which will be the smallest ellipse.
Sure.
Okay. Later on, we will do the general case where we will have an ellipse like this, and whatever we learn from this exercise will be plugged in immediately into that, and we will get the general formula. Okay. So right now we are just doing a practice exercise, but this practice exercise contains all the insights. Okay. It is not some toy problem or anything. This is the problem. Okay. Okay. So let me just postulate, or let me force you to think that the center of the ellipse will have to be here, and it will be at some point -x. If it is here, and let me also say that the ellipse will pass through this point, and it will pass through these points. Okay. So sorry. Ellipses. Okay. So it will pass through these points. So now, since this is the center and it is passing through these, and so it's all perpendicular to this x-axis. The other axes are perpendicular to this axis. Yeah, this is that little sphere, n-1 dimensional sphere that is cut off by this hyperplane. Okay, so there is this eigenvalue corresponding to this direction, and in that direction we know that lambda1 squared has to be 1 minus x squared. Furthermore, I'm assuming that the ellipse passes through this point, and it passes through this entire circle which is cut here. Okay, but let us focus on this point. On this point, the equation x transpose d inverse x, yeah, should be equal to 1. That's why the ellipse passes through this. Let us write down that equation for this. So this point has only 2 coordinates. The distance is x on this. The x displacement is x, and the y displacement is actually 1, because the original sphere was a unit volume. So this point, which is x away from here and y in this direction, other coordinates are all 0. Yeah, other n-2 coordinates are all 0, must lie on the boundary of this ellipsoid. So this equation must be satisfied. Okay, so what did I do? This is lambda2 squared. So it must satisfy this thing. So we get an equation for lambda2 in terms of x. Okay, so don't worry. I mean, this is just, I'm solving for lambda2 from this. I believe I have done it right, but we can check it. Okay, yeah. So now we are done, because by symmetry, lambda3 squared, lambda4 squared, lambda n squared, by corresponding by thinking about the corresponding point in various other axes other than this y-axis, yeah, the z-axis and the various other axes, we will get that all these are given by this one. And so, what is the ratio of the old volume, or volume of this original ball, to the volume? So I'm going to write the volume of this new ellipsoid on top and the volume of the old ellipsoid on the bottom. What we have done is we have scaled the ellipsoid by lambda1 in one direction, lambda2 in another direction, and lambda2 in the other, all the other directions. Yeah? In n-1 directions, we have scaled it by lambda2, this lambda2, and in one direction, we have scaled it by lambda1. So we write 1 minus x once, and then 1 minus x by square root of this. Yeah, so we have to take the lambda2. Lambda2 is the square root of this. So you get a total accumulation of 1 minus x n times, and this 1 minus 2x n minus 1 over 2 times. Is this clear? So see, when you scale something, the volume also scales by the same ratio. Yeah? So if you scale something 5 times in one direction, the volume will go as 5. Suppose you scale something by factor 5 in one direction, factor 7 in the other direction, the total volume will increase by factor 35. Okay, that's all. That's all we have done. Now the point is, where should you choose this center so that the volume of this ellipsoid is as small as possible? That amounts to minimizing this quantity by choosing x appropriately. You do a little calculus, and it turns out that x is 1 over n plus 1. Is everybody with me so far?
How you get the lambda is still a bit unclear, but I'll see this.
No, but let's say the question again.
How you get
I can't hear you at all, actually. How you get?
is
How do you get to?
how do you get this lambda is from x?
Yeah, so I said that, so there are various things I'm telling you, that the new ellipsoid will have its center at a point x. It will also, there will be a little circle here. Yeah, that circle will fit snugly in this ellipsoid. So every point on the circle here, or which is obtained by cutting this original ball by this hyperplane, will be on this ellipsoid. Okay, it will be passing through them. Yeah. So then, if you look at this point, it has to lie on this new ellipsoid. And if you write the equation for that, you get this. And if you solve for that, you get lambda.
Okay, so this is just for 2 dimensions.
No, any dimensions. So this point is the other coordinates.
Okay. Say its support is only on one coordinate.
Yeah, it is support. This point is supported only on 2 coordinates. It has an x coordinate away from the origin, and it has this coordinate. The other coordinate, I don't know if you're seeing my picture. They are vertical to this, and they are all are 0. Okay.
Okay. So you're saying the extremal points will always be supported on 2 coordinates.
Yeah, let us assume, or you. So by intuition, by whatever, by what should I say? Let us try this fluke. It works. It gives us this value. Then we verify that every point of your original ellipsoid, which is in this part, is contained inside this. Okay. So at least this is a valid ellipsoid which contains this half ellipsoid. So let us go on with that. Okay. Whether this is the unique minimum ellipsoid is not of concern to us at the moment, but I would be interested to know. Okay. Yeah. So we have obtained a choice for X, and we know exactly what the ratio of the new to the old is in terms of X. So it amounts to plugging in this value. So let us plug in. Yeah. This value of X in this. Okay. So if you do that, yeah. So 1 minus X, I hope, is n over n plus 1. And if you write 1 minus 2x, you will get n minus 1 over n plus 1. Yeah. And the exponents, I hope I copied correctly. Yeah. And if you do some algebra, there is 1 n over n plus 1 factor you take out here. And then what happened? Yeah. So since I've written n minus 1 by 2, I have moved this 2 inside, blah, blah, blah. Okay, good. So if you write down, in the end, you get this expression. Okay, so n over n plus 1, I can write as 1 minus 1 over n plus 1, which looks like a waste because that's what I started with. But 1 plus 1 over n squared minus 1, you redo this and you have this. Okay. Now, 1 plus z is less than e to the z for both positive and negative z. Yeah. So 1 minus 1 over n plus 1 is less than or equal to e to the minus 1 over n plus 1. 1 minus something is less than e to the this. Okay, this is a standard inequality. I mean, yeah, you will do that. I mean, e to the x is an equation like this, and 1 plus x is an equation, is the line, and this line is tangential to 1 plus x. So 1 plus x is, yeah, what did I say? Something like that. Yeah. So yes, 1 plus x is less than e to the x. 1 plus z is less than e to the z. Yeah. You can do it from this picture. Yeah. Okay. Okay. So you get these. Yeah. So again, and if you just solve, you actually, this is an equality. Okay. So this is what we wanted to prove. The ratio of the two volumes is bounded like this. Okay. Now, let me go back to Kavita's question. This is not the ellipsoid we have been given. We have been given some funny ellipsoid. And now when you have such an ellipsoid, one might have wanted them to cut this ellipsoid nicely along one of the axes, yeah, or perpendicular to one of the axes. But no, somebody has given us some hyperplane which cuts this ellipsoid through the center. Well, it cuts this ellipsoid somewhere. We shifted that plane to the center. You might remember. Yeah. So now we have this situation.
Sorry, one more question. You just ensured the extremal points lie within the ellipsoid, but how do you ensure anything that it's on this side of the hyperplane lies within this ellipsoid?
Well, actually, we have not ensured all extremal points. We have not talked about these extremal points, which is your question. Yeah. So you write down the equation. We know these points, they satisfy summation xi squared is less than or equal to 1. Yes. And you check whether they also satisfy the equation corresponding to these lambdas. We have the equation of this ellipsoid and this ellipsoid, and you just take a point which is inside this ellipsoid and on this side, and verify that it is inside this with these values of the lambdas.
Okay, but in that case, why do you use the equation of the hyperplane? Yeah.
Sorry, I can't hear you. For every
when we derive this lambda is, when do you use any equation of the hyperplane here?
Say that when we derived this lambda is, after that I didn't hear you.
So this lambda is we got from x, right? And x we just set to be 1 by n plus 1. But that does not actually even depend on the hyperplane.
Sorry, that does not depend on the
hyperplane.
Well, it was because we assumed that the hyperplane was vertical. If the hyperplane was horizontal, the point will be here. If the hyperplane was like this, the point will be here.
Okay.
Yeah. This dotted line told us which hyperplane, and it depends on that hyperplane. It is the x is in the direction which is on the negative normal. So so let us say the hyperplane was this, because we write ax less than or equal to beta. So a is this vector, and or rather ax is less than or equal to 0, a transpose x. So a is this unit vector or some vector in this direction. Let's say in this case a was a unit vector in this direction. Then we go x units along the negative of that normal vector in the opposite direction, and that will be the point. So if you give me this hyperplane, I will take its normal, normalized normal, and I will go in the opposite direction, the same x units, 1 over n plus 1 units. Yeah, we can believe that. I mean, at least in the ball, there is complete symmetry. That should be true. Yeah. Is that okay so far?
Yes.
Yeah. Okay. Now I'm interested in the general case. Okay. Now, in general, the new value of z, the new center, is the old center shifted. There is a 1 over n plus 1, but in some funny direction. And this direction at the moment, if you have not seen such numbers, is really like, I mean, I can't think of an uglier number. There is a d floating here, there is a d here, there are transposes, and there is a square root. Okay. Yeah. But actually it turns out that it's completely simple. Okay. So I'm assuming that you have not seen too many calculations like this. So I'm going to derive this for you from whatever we have done before. Okay. And this part, I will leave it to you. Okay. So this part, in this case, we knew what the new D was. The old D was the identity matrix because we assumed it was a ball. The new D was this matrix. And its values we completely determined. Yeah. One of them was 1 over n plus 1, and the others we knew what it was. Okay. Yeah. So in a general case, when we have been given an arbitrary D and an arbitrary hyperplane, yeah, then you can write down explicitly what the center of the new ellipse will be and what its new matrix of this new ellipse will be. Okay. Yeah. So let's start. Yeah. So I just want to do this derivation once. So this is the real problem. Don't look on this part. Yeah. Just look here. So somebody has given us an ellipse and a hyperplane. However, they've given us the hyperplane, they've given a vector A and told us that the hyperplane is A transpose Y is less than or equal to 0. I'm going to be using the variable Y on this side. Yeah. So, okay. So now I'm going to imagine that this ellipse was actually, because this was our original definition of an ellipse, was obtained from some ball by a linear transformation B. Okay. Yeah. So let me not worry about the affine transformation, shift of the origin. This is 0, this is 0. And there used to be a ball, and this ball, when transformed by this matrix B, by a non-singular matrix B, led to this ellipse. Okay. Somebody gave us this ellipse. We're just going to say, where did this come from? And it came from this ball by the action of this non-singular matrix. Okay. So I would like to say, well, if this ellipse corresponds to this ball, then what does this hyperplane correspond to? So let us ask. A transpose Y is less than or equal to 0. So let us write it down in terms of, so Y is Bx, right? So what did I do? Sorry, here. So A transpose Bx is less than or equal to 0. Where did I get this from? A transpose Y was less than or equal to 0, but Y is Bx. Yeah. So A transpose Bx is less than or equal to 0. So if I write this, so what is I can write this as B transpose Ax. That means the vector A here has now become the vector B transpose A. So this hyperplane, which used to be perpendicular to this vector A previously, is now, its pre-image here is perpendicular to this vector B transpose A. But notice that this B transpose A is not quite a unit vector. When we did this calculation here, and we said we have to move 1 over n plus 1 units to the left, we basically used the unit vector here, and unit vector times 1 over n plus 1 is what we moved here. So we do a little normalization here. So how do you normalize this? Well, let me just do it. So the normalization is, you write B transpose A and divide it by its length, the square root, square root, of the dot product of this with itself, B transpose A is this what it is? Yeah. Okay. You see? Yeah. So that is the unit vector in this direction, is this vector. Okay. Yeah. And so what is our new Z coordinate? So if we wanted, so forget about this, we'll come to this. If we wanted an ellipse here, which encloses this little hemisphere, in whatever, half ball, then what we should do is choose a center here, which is 1 over n plus 1 units. I made a mistake, of course. This is so you understand, this direction was A was going away from the ball that I want. So this was B transpose A, and this direction is minus B transpose A. So I move minus B transpose A times 1 over n plus 1 in this direction. And that is the center. If I were required to enclose this ball, enclose this half ball in an ellipsoid, okay, that would be the center. Now, and this ellipsoid has a volume which is smaller than the outer ellipsoid by a factor that e to the power minus 1 over some, what was it, 2n plus 2. Yeah. Okay. So I take this ellipsoid here and I apply the transformation B back, and that will result in some ellipsoid. And let's see, maybe it is this one. And that ellipsoid I don't know, it's not moving properly. Yeah. So I first build the ellipsoid here. And transform it back. Now the ratio of the volume of this, smaller ellipsoid to the outer ellipsoid has been calculated, but a linear transformation will maintain the ratios of the volumes. If some volume got changed by a certain factor, the other volume will also get changed by the same factor, which basically comes out of the determinant of this linear transformation. Yeah. So now let us see where we should place the center of this new ellipsoid. So the center of the parent parent ellipsoid here is this, which we know is this. Okay, so what does this look like? You recall that this quantity B inverse transpose By is less than 1. This B inverse, so this B was related to B by B transpose. This we did last time, and you can also read it out of this equation. Yeah. Okay. So D is BB transpose. So this BB transpose here is actually the D, which starts looking like that ugly formula that I wrote before. And there is a B transpose here. But if you see, what we have here is D, not B transpose. But this is the point Z nu on this side. What is its corresponding point on this side? Well, you multiply this by B. Yeah, and you get this. Is this clear? We wanted to find the best ellipsoid on this side. We said, no, we will not mess around. We will go to our familiar case of a ball, transform everything, so to say, by B inverse or something. Yeah. So we find out what the structure is here, use our previous knowledge to locate the center, and then translate the center back here. Yeah. Notice that it is not just traveling back in the direction. In a sphere, when you have a hyperplane, the center is located just in the opposite direction of the normal of the hyperplane. But if it's an arbitrary ellipsoid, yeah, this was the ellipsoid and that was this. What you go in the direction B transpose A. You don't go in the direction minus A. Sorry, you go in the direction DA. You go in the direction DA, not minus A. Okay, so it will be some, I'm sorry, it will be some direction like this, and this is where the center will be. Okay. So I've said, where does this equation come from? It comes from such considerations. I would like you to do the same thing to get to, we know the familiar D nu in the case of this situation, but morally, that situation and this situation are not different. They are all related by this linear transformation B. There should be a back and forth argument which should tell us that the new D ought to be this. Okay, I will let you do it. Questions? Okay, but this was just to get you somewhat familiar with what sort of calculations go on. It's not key to the underlying principle of ellipsoid method. Questions? Okay, so I want to spend about 10 minutes or so dealing with the assumptions that we started with. So we assumed that
why did you use the fact that we are querying the center of the ellipsoid in the previous step?
Say that again. Where did we use the fact that
we queried? We found a point. We found the hyperplane which separates the center of the previous ellipsoid from the polygon.
Yes, and it is because it was the center. It was passing through the center. Here, this cut.
Okay, so we could analyze the unit for this step.
That's right. This center is this center. This hyperplane is not still the same hyperplane, but it's some slightly tilted hyperplane. Yeah. But notice that the original cut here, yeah, you might call it was not a very kind cut. It was some strange cut. Yeah. But nevertheless, when you transform it here, no matter how awkward the cut looks here, as long as it passes through the center, it becomes a nice cut here. It is always cutting the sphere into two parts which are as symmetric as you could ever get. Yeah. Whereas here, it might look a little awkward.
And here you also never use the fact that this hyperplane, there is an objective function in the equation for the hyperplane.
No, we have just used the fact that somebody has given us a hyperplane passing through the center of this ellipsoid, and they want us to enclose half ellipsoid in a new ellipsoid. And we have found out what a candidate new ellipsoid is going to be. But yeah, you should be convinced at least that the ratios will still be that e to the power -1/2 and +2.
Yes.
And its center also, I hope I convinced you, will be this. But in our computation of the ellipsoid method, we will be dealing with the actual ellipsoid's representation, for which we also need the associated positive definite matrix. And the transformation of the positive definite matrix, when somebody has given us an A, is this formula. Okay, and this is something I want you to verify. Questions? No, no questions. Yeah, I hope that everybody is there. Okay. So we assume that the polyhedron is bounded and full dimensional, and because we wanted to first enclose it in a ball. Yeah. So, but our goal is to find a feasible solution to this system of in this system of inequalities. Okay. So the question is, how do we ensure that it is bounded? Well, see, if this, let me write something. Yeah. So if this system has a solution, let us just turn it into our familiar simplex type of thing. So we write it as ax tilde less than or equal to b by adding some slack variables. Yeah. And somehow something like this. Yeah. So what was this has now been turned into this. Maybe we augment this A by some additional matrix, etc. So we are interested in finding a feasible solution to this. Yeah. So let us just observe. We will be working with this. We are not going to change the system or anything. Just for the argument purpose, I'm saying to find a feasible solution to this, we might as well find a feasible solution here. Sorry, here it's become equality. Yeah. Remember in question. Sorry,
that should be an equational form.
Yeah, thank you. Yeah, sorry. So yeah. So this has become an equational form. Very good. Yeah. And now we have studied that in this equational form, if there is a solution, there is a basic feasible solution. In other words, you remember how we did that. If you look at this some feasible solution, if the columns corresponding to the support of that feasible solution, wherever that feasible solution has non-zero values, if those columns are not linearly independent, then you can shift this point along a line which is in the kernel of this matrix and knock off one more entry. Okay, and that way eventually we can assume that the vector that we have here, the non-zero entries of this solution correspond to columns here which are linearly independent. Okay, that means this equality has a unique solution. That means if the original system had a feasible solution, there is a feasible solution whose support corresponds to a set of linearly independent columns, which means we can solve for that x by Gaussian elimination. And in your homework, you have proved that Gaussian elimination is an efficient method, which means if the entries of this matrix, so how did we get this matrix out of this matrix? Well, we probably added an identity matrix and did some other little manipulations. So in the end, this matrix is entries and this matrix is entries. Yeah, their values are not very different. You have just added some ones, etc. So they are still bounded. Okay, if the original ones were bounded by some phi, maybe this is also bounded by phi. And now you can find this solution x tilde, and from that extract the solution x by doing Gaussian elimination. And Gaussian elimination is an efficient process. And so from that you can conclude that if there is a feasible solution to this, then there is one where all coordinates are actually bounded. Yeah. So let me just write it down. So we may assume all so you remember we had defined a value nu. So it turns out that if you did this calculation with determinants, etc., in the end, you will be able to conclude that all these, there is a feasible solution here, all of whose coordinates are bounded by this number. Okay. So what you do is you just take this system of inequalities and add more inequalities which look like, sorry. So when I say are at most new, I mean at most new in absolute value, of course. Yeah. That means we just put this polyhedron and cut it off by a box. Yeah. By a box of some. Sorry, I should really write. So is bounded by some r. So the number, each coordinate is bounded by some value like this. So
that is minus r, right? In the left.
Sorry, yeah. Thank you. Yeah. So minus r to this. So it becomes a box, and we are now in the bounded situation. Is this clear? So you look at the system of inequalities that you have got. From that, you think about it either in this way or in some other way, and find out that if there is a feasible solution, yeah, there is one whose values are at most this. Okay. And you say, I will now work inside that box, and the size of this radius is only 2 to the power some number like this. Yeah. And that also fits in polynomially many bits. So we are not going out of control. Is this clear? So this takes care. Yeah.
This is to justify the square root operation.
No. This is because we start our ellipsoid method by putting the polytope inside a ball. So, okay. I mean, people could say that your Kachian cannot even start because we need an initial ball with some radius r, which contains the polytope. Yeah. So at least we can start. Okay, let's see. Next question. Why is it full dimensional? Okay. Now, especially when you did simplex method with so many equations, yeah, if you impose an equation on a system, yeah, so it will not be full dimension. Yeah, you are going to cut it off. Yeah. So what do you do? Okay. So the idea is that when you have an equation like this AT, we are going to say that we are going to add a little bit of epsilon to the right-hand sides of these equations, these inequalities. But the epsilon will be very small. So what do we want to ensure? That if
it contains we want to insert contents as sphere, right?
It has to contain some small sphere, but that is not how we have said. We have just said that it should be full dimensional. Okay. Yeah.
Okay.
But the question is, maybe the original system was infeasible, and the moment you increased this right-hand side by epsilon, it has now become a feasible solution, feasible system. We don't want that. Yeah. So we want to ensure that the original polytope continues to be inside the new polytope that we are constructing by fattening it. But if the original polytope was infeasible or was empty, then the new polytope should also be empty. Okay. So we have to choose this epsilon. And now let me just give you the idea. Yeah. See, suppose there was a system of equations, inequalities, which was infeasible. So there was this inequality, sorry. And maybe there was, and there was this inequality which said, yeah. So what do I mean? This inequality says your point must lie in this side. This inequality says your point must lie on this side. And this inequality says your point must lie on this side. This is a system of inequalities which actually is infeasible, because yeah, the region described by these two hyperplanes is disjoint from the region described by the third half space. Yeah? But here you see, there is a little bit of a slack. It is possible for us to perturb each of these hyperplanes, yeah, relax them a little bit, yeah, make them slightly relaxed, and still it will remain infeasible. Okay. So the point that we are going to make is that if your original system was infeasible, it is possible to perturb the right-hand sides, yeah, so that it continues to be infeasible. And the amount that you perturb the right-hand side can be calculated based on the numbers that you have. Okay. So, yeah. So first of all, how do I think about this? Yeah. So if the original system is infeasible, so let me write down, and I don't know why my pen is so fat. So the original system, AX less than or equal to B, is infeasible. Yeah. What does that mean? That means it is possible for me to derive, multiply these equations. So this you can call the Farkas lemma, or something that we proved out of Fourier-Motzkin. Yeah. So we can find these multipliers so that, of course, you get this. Yeah. We can derive the inequality 0 less than or equal to -1 from this. If this was infeasible, then we can derive this inequality by multiplying this by suitable y. Okay. So this y, yeah, this dual solution is a witness to the infeasibility of this. Okay. But actually, this y will also guide us in determining the epsilon by which we can perturb and still stay infeasible. Now imagine that we have added epsilon to the right hand side. By that I mean epsilon, epsilon, epsilon. Yeah. So suppose I added epsilon, epsilon, epsilon to the right hand side, and I use the same dual witness. What would I get? On the left hand side I would get 0. On the right hand side I will get -1. And then, sorry, I should write it down. So if I started from these inequalities and multiplied them by the same witnesses, what would I get? On the left, I would continue to get 0. And on the right,
Y transpose B plus epsilon.
Y transpose B is already known to be
-1.
-1. And basically, I will get Y transpose and these epsilon. Yeah. So this y is with me. There is a y, okay? And we'll find out what that y should be. But once somebody has given us a y, we can tune this epsilon so small that this y, when multiplied by this epsilon, does not eat up this -1. That is, the right-hand side continues to be negative. And if the right-hand side continues to be negative, then the same y is a witness to the infeasibility of the new system. Is the point clear? If we can find a y which witnesses the infeasibility of the original system, and we know that there is such a y, using that y, we can calibrate the epsilon so that the new system, even if these hyperplanes are shifted a little bit, yeah, they will continue to be infeasible. And this epsilon, how do we, okay. So now the question is, how big can we make this epsilon? Yeah. So, I mean, we should not make this we should keep this epsilon reasonable, because in the end, our entire calculation of ellipsoid method depended on the binary representations of this epsilon. So can we get an epsilon which has a reasonable binary representation, and still this system remains infeasible, and now it has become a full dimensional system, okay? Because the original feasible solution has space all around it, because no inequality is cramping it up. Everybody is away, yeah? So you will have a ball of some reasonable size around it, okay? But how small can we make, how large can we keep this epsilon and still hold this? That depends on y. So unless y's coordinates are too big, yeah, if y is 1 million or something, then epsilon can be only 1 over 1 million, because it should not eat up this -1. So what tells us that y should have reasonable coordinates? Well, what is y a solution to? Y is a solution to this system of equations. Y transpose A must be 0, and Y transpose this B should be -1. So we can write A transpose, I don't know, yeah, and B somewhere, and write Y, yeah. So A transpose and B and Y, 0 and -1. And we know that this system, if we find a solution Y to this system of this, yeah, that would do the job for us. Well, the same argument works. This system that we have written here has numbers which are reasonable. It has a solution, just like we did for finding out this R. It has a solution where the binary bit lengths are not too large, and we are done. Okay, so is it clear? So all we need to know is whether a system of inequalities is feasible or not. You remember last time we said, if you can tell me whether a system of inequalities is feasible or not, okay, then you can solve the LP. Yeah. So we start with the system of inequalities. It is not full, it is not bounded, we make it bounded. It is not full dimensional, we don't solve this, etc. We imagine that there is a solution, and we know that that solution will have bounded size. And from that size, we estimate an epsilon, and we just go ahead and perturb this by changing the right-hand side, increasing the right-hand side by epsilon, and then hand this system over to the ellipsoid. Now it is bounded, and it is also full dimensional. All right. Okay. So now, question.
One question. Should all the epsilon's value will be same? Like,
yeah, we will put the same epsilon, maybe the smallest among, yeah.
okay.
Yeah, we'll use the same epsilon for all of them.
So Jaikumar, I have a doubt. In claim 2, we said P has a certain volume also, right?
Sorry?
In claim 2, yeah.
Yeah, P.
Yes.
If P is coming out of a system of inequalities where all entries are bounded,
Sure.
P will automatically have this volume, is what we proved. So we had the original system where the numbers were bounded, that is AX less than or equal to B. This was given to us and the numbers were bounded. To that we are adding this. So think of this as the new system of inequalities, And this also has bounded right numbers now. So the new system will have the numbers which were there before, and in addition, these numbers.
But P could be empty too.
Sorry?
Could be assumed to be infeasible too.
Sorry, so if it is infeasible, so we do these many steps, and if we cannot find the point, we will declare it to be infeasible.
Oh, okay.
Sorry, once again, I was, so I was always assuming that the ellipsoid is feasible. The system was feasible. Let me say this again. Here is Khachian's algorithm. Given a system of inequalities which satisfies these assumptions, it will run for a certain number of steps. At the end of that step, if it has not yet found a point which is feasible, it is going to declare the system to be infeasible. Because if the system was feasible, the polytope would have contained enough volume and we would have stepped into it. The fact that we haven't yet stepped into it means that the original system was infeasible.
Thanks. Sorry, I got confused.
No, I didn't make that point. Yeah, so thank you. And we are working with a new system, but we need to be careful that when we added new inequalities, we should not add new inequalities with numbers which are humongous, because the old analysis depended on all numbers being reasonably in size. And this calculation tells us that the epsilon that we will choose will depend on how big y's are, and we know that y's arise out of the solution of a system of equations, which unfortunately has vanished from here. Is that okay?
So given A and B, is there any condition which implies when this polytope has full dimension?
We cannot really be sure directly. Yeah, I mean, there can be a condition, but it might also involve solving a linear program, the dual program or something.
Okay. Is there any way to convert non-full linear programs to full dimension?
Yeah. So once again, if the original system was not feasible, I mean, we would like to keep it infeasible. And if it is feasible, we would like to fatten it to become full dimensional. And this is the way. And this is the way to do it. Just relax your right hand sides.
So Khachian's method says you always add epsilons.
You start with ax less than or equal to b. You are all worried that it might not be full dimensional. So you do this, estimate what sort of numbers y would be based on the other numbers that appear in A and B, and put an epsilon here on the right hand side so that it becomes a little fat. This p you add, make it p epsilon, p with the right hand side relaxed by epsilon, and now continue.
I see. Thanks.
Okay, so I'm sorry, I'm very slow today. I'm saying the same thing over and over again. Now, the other problem was that other assumption was we are doing everything very precisely. Sorry, I don't know where my assumptions went. I wrote the assumptions again, right? Yeah, I don't know. There used to be assumptions. Yeah, here. Yeah. So these calculations can be done precisely. Now, of course, there was this, square root, which we now fully understand. Yeah, but if usual simplex method, etc., what we were doing was with rational numbers. Yeah, so even if the original matrix didn't have rational numbers, in the course of various scalings and subtractions and clearing out some coefficients, we would have been led to rational numbers. But the rational numbers that arise in the course of simplex method, yeah, because we are just doing Gaussian elimination, multiplying. Yeah. So you can check that all the numbers that arise, because at any moment you have a certain basis and you're multiplying the right-hand side by the inverse of that basis or something like that. Numbers will all be, reasonable rational numbers. And you have proved in your homework that the numerators and denominators of those things will stay bounded. Okay. But here we have to do things like square roots and other things. And you can only do it to certain precision. Now, when you do things to a certain precision, the center of the new ellipsoid that you compute, yeah, and the D, the matrix D that you compute, they will all not be the original D, the perfect D that you want, but they will be Ds which have been slightly perturbed, depending on how many bits of precision you choose. And sometimes things can go wrong. Yeah. And so one needs to work to make sure that all the approximations that we do, yeah, keep things under control. So, as I said, I'm not going to tell you what theorems give us the necessary, so I'll show you the theorems, but we are not going to apply it and make sure that everything is okay. Okay. So so there will be two theorems in the notes. I will just quickly tell you what they are and then move on. Okay. So the first theorem says that suppose there was an original ellipse and now you have truncated the numbers to p bits of accuracy. By that I mean, sorry, Srijatu cannot hear us. Can anybody hear me?
Yes.
Yes, we can hear you.
Okay.
Yes.
So, yeah, can somebody reply to Srijatu that he should set his connection right? Srijatu, can you hear us now? We can't hear you, of course. I don't understand. I think he's on campus. I don't know why his connection is particularly bad. Yeah. So Srijatu, I'll continue. I don't know what happened. So anyway, so here is a number. It depends on the largest eigenvalue and the smallest eigenvalue. Now be careful. The smallest eigenvalue will be a very small fraction. Yeah? It will be some number like 1 over k. Yeah. So that k, sorry, what did he say? Okay, yeah, he's fixed. Okay, so this s, yeah, it might be a fraction with a huge denominator. Okay, so even though it's a small number, its binary representation can be large. Yeah, so you look at the binary representations of the smallest eigenvalue, the binary representation of the largest eigenvalue, and there is an epsilon which will be used in our calculation. Yeah, and suppose you truncate all numbers. Yeah, that means there is a decimal number. When you write binary representation, there is a decimal number, and you go p bits to the right and you truncate all numbers. So when you compute square roots, etc., you make sure that the first p bits after the decimal point are all correct. Then, instead of working with the original ellipsoid, we will be working with this ellipsoid, given by the new center, approximate center, and approximate positive definite matrix. Okay. It will turn out that if you did this, the new eigenvalues are not going to be too much different from the original eigenvalues of this matrix. Okay. And the new ellipsoid that you construct might actually be bigger in some places than the original one. Yeah. It might shoot out of your original ellipsoid, but if you take the original ellipsoid, let me draw it here. You took the original ellipsoid and then you drew a little fattening of it by epsilon. So this b e tilde epsilon, sorry, it's the other way. You took the new ellipsoid and you fattened it by epsilon. That will include the old ellipsoid. I might have said something the other way. So the old ellipsoid may not be contained in the new ellipsoid, but a little fattening of this ellipsoid would put the old ellipsoid inside. And remember that, see, the whole Kachian method works because each time we get smaller and smaller ellipsoids. But then if we are going to be forced to fatten some ellipsoids, then the gains that we got by putting a new ellipsoid around the half ellipsoid might be sort of erased by this epsilon. The point is that this new ellipsoid, this approximation doesn't make it too much bigger. So this epsilon, we will choose to be much smaller then that 1 over 2n plus 2, etc. So despite these approximations, the new ellipsoid that we will construct out of being lazy about our computations by rounding will still stay in control. Okay, so how this gets used, I'm not going to say. Okay. The other problem is that yeah, so my semi-definite program is not going to happen today. But anyway, so let me say one more thing. Suppose you have a line like this, and there is another line, and they have this point of intersection. Yeah. Okay. Now, so there is this feasible point, which is in this, belongs to both these lines. Now, suppose I chose to fatten one of these lines. Yeah. Then there is a point which is common to the fattened region and the old line, and that point is slightly away. Yeah. And one can imagine that if I fattened, or one might normally think that if I fattened a line only by epsilon, the other feasible point cannot shift too much. It will be pretty close. Yeah? If original point of intersection was this, now I have fattened this line, how far can it go? Unfortunately, I mean, this picture is misleading. What if the other line was like this and I fattened it? And how much has the point shifted? From here, now I find a new feasible point which is far away from the old feasible point. Now, you should think of this second line that I drew as some kind of a degenerate, this line, as some sort of a degenerate ellipse, okay, where the smallest eigenvalue and the largest eigenvalue, sorry, I don't know why I wrote 2s squared here. Okay. Anyway, yeah, so the smallest eigenvalue and the largest eigenvalue are very well separated in ratio. But suppose all eigenvalues are in this range, then if you take the ellipsoid, yeah, instead of this line, it was an ellipsoid, and you fattened it. Yeah, so you took the ellipsoid, you fattened it by epsilon, and look at its intersection. This object, yeah, you fattened the ellipsoid and saw what all points. So you fattened this line, and then we took the intersection with this line, we got these points. Yeah, that is this left-hand side. It is contained in the original intersection. And of course, it depends on epsilon, but you need to scale this epsilon by the ratio of the largest eigenvalue, square root of the largest eigenvalue, and the smallest eigenvalue. So if your original epsilon did not have very different, or the ratio of the largest eigenvalue and the smallest eigenvalue was not too bad, then this sort of approximations do not take your feasible point too far away. Okay, and this will have some consequences. I mean, when we analyze ellipsoid method, I don't expect you to immediately see where this might get used, but theorems of this nature need to be proved to fully justify the ellipsoid method. Okay, so I'll stop here. I'm really sorry if I tempted you to come by saying semi-definite programming, but I have those notes from linear to semi-definite programming. The important thing is this. Okay, in ellipsoid method, in each step, what we needed was a hyperplane which would tell us on which side we should look for the solution. Okay. And then we fit a new ellipsoid and all that. Those are details of the ellipsoid method. So if we are trying to optimize over any domain, where whenever, or we are trying to find a feasible point inside any domain, yeah, in our case, it is polytope. In linear programming, it is polytope. But inside any domain, where when presented an infeasible point, somebody can provide us a hyperplane which separates the infeasible point from the domain, then ellipsoid method is applicable, provided we could put an initial ellipsoid around the domain. Okay. Now, this happy situation happens in when we are trying to optimize over things which are not polytopes but cones of positive semi-definite matrices. So it turns out that if you look at all positive semi-definite matrices, they form a cone, yeah, which is not hard to see. Yeah, we'll talk about positive semi-definite matrices if you've seen it in your linear algebra course. So we would like to find a point inside the positive semi-definite matrix, yeah, which satisfies some linear constraints. Okay. Now, whenever presented a point which is not inside this positive semi-definite matrix which satisfies these linear constraints, we would like someone to come up with a hyperplane which separates this point from the feasible solutions. Okay. Now, this the cone that we are talking about in the case of positive semi-definite matrix is not even finitely generated. Okay, it's some sort of a smooth body. Nevertheless, linear algebra, which we'll do next time, tells us that whenever there is a point outside, it is possible to efficiently find a hyperplane which separates it, which means ellipsoid method is applicable for solving those sort of feasibility questions, yeah, but only approximately. Okay, so all those subtleties will come up next time. First, I have to tell you, so the upshot of that is there are efficient polynomial time algorithms in principle for this object called semi-definite programming, in addition to linear programming. Yeah? And we will, so it is worth studying semi-definite programs for combinatorial problems. And that is what the rest of the course will be devoted to. Okay. So I'll stop here and tell you about semi-definite programs next time. But you are welcome to read the notes and make whatever you can of it. Questions? So what did we do today? Basically did what we did last time. I showed you a little bit of a calculation about going back and forth, told you why we can assume that the system is bounded, why we can fatten the system. And this fattening of the system had this, in my view, a very charming use of duality. Okay, how much you can fatten a system, yeah, is guided by a dual solution, which we don't need to find, whose existence, and especially that it exists with bounded sized entries, is all we use, yeah, to fatten the system. Yeah. So dual solutions have a role to play in linear programs, certain aspects of linear program called sensitivity analysis. How much does the optimum change when you relax one of the constraints? Okay, or which constraint should you relax? Yeah, you might imagine in economics, yeah, so how much should you reduce the tax or something to create some other equilibrium? Yeah. So these sensitivity analysis has, I mean, dual variables have a role to play in sensitivity analysis of linear programs. We have seen a particular extreme case of it where we are using dual variables to analyze feasibility and infeasibility under relaxation. Sorry, too much philosophical. All right. So I would really encourage you to read Shriver's book, this chapter. Yeah. And also, but before that, read our own text, Martushek and Gartner. And it points to literature where the details are available. The book itself doesn't give all the details. All right. If there are no questions, thank you for listening. Bye.
Thanks.